I had asked the question to draw the velocity time graph for a certain motion, right? The last class, that was how we finished it. So when I throw the marker up and it comes back and lands on my hand, how do you draw the velocity time graph? And did you all manage to do it?
No.
Not yet. So I'll tell you, some of you have drawn this graph. Some of you drew it like this. Now, what does this graph actually mean for the marker? This is how it means. It is at rest in my hand, and then for some strange reason, it just starts off slowly. It starts with 0, see? It starts with 0 and starts accelerating like a rocket. And it keeps going and keeps going faster and faster. When it reaches that speed, it slows down and slows down and slows down and stops. That's it. End of story. Is that what it is? No, this graph does not relate to what you're thinking about. So what is the graph then? Yeah.
Is it when you start from a point above 0?
Okay, so it starts from here. Some of you have drawn this. How many of you got this one? Now let me explain this graph to the real world. How is this one? Yes, the first one is right. I threw the marker up with a positive velocity. Can you see that? Why is it positive? Because it's upward. Now if I threw it downwards, it would be like a negative velocity. Yes, I threw the positive velocity. And what happened to the velocity as it starts moving up? It is slowing down, stops, and starts off again. So that's what this means. So are you getting close to the answer then? So what is the real answer?
It should start from the same point and then just keep going down.
Exactly. That is correct. It should start from this same point with a positive velocity and then go up and come back. So that is the appropriate graph for this particular motion. This particular motion, that's a graph. For velocity time, yes.
So, kind of in the other way, let's just say yo-yo. If you're throwing it down, you stop and then you go start in the negative.
In the case of yo-yo, it is not purely under gravity.
Okay.
You're pulling it, so there is a kind of tension that's building up, right?
Okay.
So when you throw it down, let's say you're throwing it down, yes, it is going with a negative velocity. It starts from here. And what happened to the velocity as it goes down? It slows down, right? It slows down and finally slows down to a halt. And then what happens after that? It is pulled back up. So it is something not with gravity's help, it is with the tension. Yeah, so that is a different story. Okay? Now, how do you know if something is having a positive displacement or negative displacement? Displacement is actually the change in position, right? Now, if you try to look at it, so this is your, let's say, x-axis and y-axis. Suppose this is my initial position. This is 1 meter. That's my initial position, so I'll call it xi, initial position. And then if this is my final position, xf, which is 3 meters that way. What is the displacement? The displacement, which is basically the change in position. Change in position. Any change is always supposed to be final minus initial. Try to understand that. If you're talking about any change, it should be final minus initial. Like for example, look at the stock market. The price of something is here, say 200. And after 2 days, the price went to 210. So what is the change? Positive 10. Why? You take the final 210 minus 200. It's a positive 10. And when you write positive 10, the reader will understand it went up. Now suppose it was 200 and then it went down to 170, negative 30. And the way you read it, negative 30 implies that it has gone down in value. You understand that? Anything going up is a positive change, going down is a negative change. So change is always final minus initial. And in this case, it is a position. So it is going to be xf minus xi. That's always the change. The displacement is always measured this way. Okay? So it was here, now it is here. Now you don't have to stick to this equation, but I'm just showing this one. So what you need to know is from this point, has it gone a positive displacement or a negative displacement? And logically, how much is the displacement? Negative 4, that's it. But if you want to do it mathematically, xf is minus 3, and this minus is right down there, and xi is 1, so it is negative 4. So the displacement is negative 4, implies that it went backward. Is it clear? Some books actually, keep writing xf and xi and all those things continuously. I don't do that. Displacement, I call it just x. Trying to minimize things. So some books actually is harder for the students to read and understand because they use so many variables. And because you use so many variables, students kind of give up on those, the scary look of it. So I try to use a minimum number of variables. So you'll see I won't use delta at all anywhere. Although it is delta. Like time, it's not just t, but it's delta t. But if I introduce delta t, and if I have to square that, delta t square makes it more confusing than just t square. So I will write the symbols in a much simpler way so that you'll feel like, okay, this equation is easy to understand and easy to follow. What is displacement? I'll write it as x. Whether it's going up or down, always is going to be x. Okay? Always I'm going to write it as x. So acceleration, I'm going to write a. Displacement, I'm going to write x. But for other things, I'll use subscripts and I'll use that. All right? So try to understand the concept of displacement. Now let me just quick recap on what we've done. So this is displacement time graph. That's displacement time graph. What is the slope of this line? Velocity. Is that clear? So if it is like this horizontal line, it is 0 velocity, positive velocity, negative velocity. Wherever it is. Well, you don't have a negative time axis. Okay? So wherever it is, you look at the slope and decide is it a positive velocity or negative velocity. And if it is down here, that means it's beginning from a negative position. That's all. Okay? What about velocity time graph? On a velocity time graph, what does the slope imply? Acceleration. So what is this acceleration? Suppose something is moving like that. This velocity, I'll call it initial velocity. And this velocity, I'll call it final velocity. And so it is moving from this velocity to this velocity in a time t. Yeah.
It's accelerating constantly.
It is. Whenever you see a straight line, it is accelerating at a constant rate. In fact, we're going to set up some equations, and all those equations are for uniformly accelerated motion. You get it? We're going to talk only about uniformly accelerated motion. If it is non-uniform acceleration, it is difficult to work through that problem. You've got to do it in segments. Like if you're taking a car from here, starting to speed up, somebody comes in between. So you apply brakes, again starting to speed up. And if it is changing like that, at what time you're going to be there is quite tough. So you may have to break those into different segments and then work through it. All right. So all the stuff that you're going to learn in this kinematics chapter is concerning uniform acceleration, straight lines. Okay? We're going to talk only about uniformly accelerated motion. So this is a uniformly accelerated motion. So we are going to study the equations of uniformly accelerated motion. We call it just equations of motion. So what is this equation of motion? Equation of motion is something that helps you to know when and where an object is, how fast it's moving at that moment, and all that stuff. Okay, that is the purpose of equations of motion. Let's say I'm just going a step further. If I toss a football at a certain speed, at a certain angle, and if I ask you exactly after 2 seconds, where is the ball? How fast is it moving? Well, at this point, you cannot answer it. Okay? You're not learned enough. But very soon, in a month, you'll see how you're going to answer those questions. You can answer them. How? With the help of physics, yeah, but there it is. Equations of motion. So what is an equation supposed to do? An equation is supposed to solve puzzles for you. In math, you have solved puzzles. Like you're given something, this is so many times this, and so on, some kind of puzzle. Or sometimes the tens place is 2 times the ones place, and the sum of this is going to be this. You know, you're given something. And so based on that, you set up an equation. And then you solve for that number. You will get that number exactly. In math, you do it. People call it problems, but I'll call it puzzles. Same way in physics. When and where, how fast something is moving at a definite time is all solved by equations of motion. Now, the equations can be different types. You know what is known as a linear equation, right? A linear equation is only one variable. A simultaneous equation will have 2 variables, like 3x minus 2y equal to something. That is a simultaneous equation. When you have 2 variables, you need 2 equations to solve it. When you have 2 variables, you need 2 equations to solve it. When you have 1 variable, 1 equation is enough to solve it. If you have 3 variables, 3 equations are needed to solve it. So it depends on the number of variables. The more the number of variables, you need that many equations to actually solve it. So simultaneous equations, you cannot solve with 1 equation, you need 2. You write both of them, and then you can use substitution method or elimination method. Does it make sense? Have you done it? You can do substitution method. Replace the y in terms of x into the first equation from the second equation and solve it. Or you have x minus y equal to this, x plus y equal to this, so just look at it, add them up. When you add them up, one of the variables is gone. And you're left with only one other variable, and so you can solve. That's called elimination method. So simultaneous equations can be done with elimination method. But equations are not supposed to be looked at with scare. Okay? Take your calculators. Take your calculators. I'm going to give you a puzzle. Alright, so this one, what is the acceleration? Acceleration is the rate of change of velocity. So it's basically change in velocity over change in time. So what is the change in velocity here? Now, we can call it average acceleration, but average acceleration and acceleration instantaneous, they're all going to be the same because uniformly accelerated. So therefore, it doesn't matter whether you do instantaneous acceleration or an overall average acceleration, it doesn't matter. So that's why if you write acceleration, it's understood. But if something is moving up and down, then we have to talk about average acceleration, which is final velocity. So this one is final velocity. So it's final velocity minus initial velocity over time is supposed to be equal to acceleration. This is one of those equations of motion. That is one of the equations of motion. Acceleration is equal to Vf minus Vi over time. That is acceleration equation. Now, what we do is instead of using this equation straight away, we cross multiply it and get it into a straight line. We don't want anything in the denominator. So cross multiply it. So we have VF minus VI is equal to AT, and then we get VF is equal to VI plus AT. This is one equation of motion. Is that clear? Now, so the acceleration definition is what brings you the first equation of motion. It gives you a connection between VF, VI, acceleration, and time. All right. Now, to get the second equation of motion, watch what I'm doing. Suppose something is moving at like this. If something is moving like that, what is the acceleration? Zero acceleration. So suppose something is moving at a certain speed v for a particular time t. If something is moving with a speed v for a particular time t, let's say for example this is 20 meters per second and it's moving like that for 5 seconds. How far has it traveled? How much? 100 meters. It's so easy, right? If something was moving at 20 meters every second and it went on like that for 5 seconds, how many meters can it travel? In every second it's covering 20 meters. So 20 meters and 20 meters and 20, so 100 meters it is covered. So what he did is 20 times this. This side times this side. What is that geometrically to this shape? Area. So basically the area of this, or under the line, area is equal to displacement. The area is displacement. So traveling at 20 meters per second for 5 seconds, you got this, and the area stands for displacement. So once again, let me ask you, what's the slope of velocity time graph? That will give you acceleration. What is the area under line? Displacement. Area under the line is displacement. Now, what if it is not zero acceleration? So suppose you have a line like this. Suppose you have a line starting with initial velocity vi and it goes on till vf in a time of 5 seconds. Suppose it starts with 10 meters per second and goes on for I'll take it off for a moment. I'll come back to the graph for this one. Suppose it's going to 40 meters per second from 0 in 5 seconds. So if an object starts from rest and accelerates, this is acceleration, uniformly to 40 meters per second in 5 seconds, how far did it travel? How much? How do you find the displacement? So find the area under the line.
So it's 100.
It's 100 again. So if it started from 0 and went speeding up to 40 meters per second in that time frame of 5 seconds, it is still traveling 100 meters. What do? Find the area of this triangle. So half base height. So half of 5 times the height of this thing is 40, and that will be 100 meters. Get it? So area under the line gives you displacement. Now let's come back to this. It's starting from here and going to a final velocity v. So from vi to vf, it's going in a time of t. I'm generalizing it. I'm generalizing now. If it's going from here to there, if it's going from this speed to that speed in a time. Oh, by the way, look at the previous graph again. I'm forgetting it. Look at the previous graph again. That's 40. That's 5. And the graph here, if I draw it on here, it is this. The area of this rectangle and the area of the triangle are the same. You can see that this triangle and this triangle kind of compensate. This triangle, folded and put here, should be cancelling out. I've not drawn it perfectly. Because that is 20 and that is 20 should be, 40 should be something. So, this area and that area are exactly the same, even though the velocity is changing and it is accelerating. Look at this one now. This is Vf, this is Vi, and time is t. How do you find the displacement? Area. So find the area. How do you find the area? What shape is this? Yeah.
You split it up into one triangle.
You don't have to. What shape is that? It's a trapezoid. What's the formula for trapezoid area?
Base 1.
Half base 1 plus base 2 times the height. Now, what are called base 1 and base 2? What's special about what is called a base? They should be parallel. Perfect. The parallel sides, they are base 1 and base 2. So this is one parallel side to this. So those are the bases. The height is the gap between the parallels. You can have any trapezoid of any, you can have it like that. This is base 1 and base 2, and that's the height. Okay? Fine. So if I use this, what is base 1? Vf. And what is base 2? Vi and times. This gives you displacement. I said already, x stands for displacement. I don't want to write it as xf minus xi and all that stuff. Okay? X. What is it? Displacement. This is another equation of motion. These equations of motion should be like memorized. Once you know where it's coming from, there is no reason why you cannot memorize it. I mean, you can't make a mistake. So areas have B1, B2. In case you lost the equation, go back and fetch it like this. Because you know where it's coming from. I will never throw an equation and say, all right, that's how it is, memorize it. No. Whatever equation I'm going to put down here, I will give you the proof as to why the equation is such. Okay? X is equal to half Vf plus Vi over 2. In other words, what? In other words, X is equal to Vf plus Vi divided by 2 times time. X is equal to Vf plus Vi divided by 2 times time. And Vf plus Vi divided by 2. Vf is here, Vi is here, divided by 2. So what is this and plus this divided by 2? That, right? The mean, average. So this is Vf, this is Vi, and the middle is this. So if I, instead of going from Vf to Vi, if I had traveled like this, I would have gone the same distance. So what is this? It's Vf plus Vi divided by 2. And you travel for the same time. Look. So this rectangle here should have the same area as a trapezoid. Good? So that's so we can also write this as x is equal to average of velocities times time. Average of velocities times time. And this applies only to uniformly accelerated motion. Keep that in mind. If it's a curve like that, you can't use it. If you're going to draw a curve like this, you can't use that as the average. Okay? So average of velocities times time. So Vf plus Vi divided by 2 times time. That is your equation. I'll call it the second equation of motion. Any questions at any point? Let me know. Okay? So the equations that we have got so far are Vf is equal to Vi plus At, and that comes from acceleration is equal to Vf minus Vi over time. So this equation actually comes from there. So I'll call it, there's no international numbering for those equations. I call it equation number 1 because that's the first thing that comes out, right? Through the definition of acceleration. From the definition of acceleration, you got that equation. And then from the definition of displacement, which is the area under the graph, I got the next equation. X is equal to Vf plus Vi divided by 2 times time. That is going to be, I'll call it equation number 2. Why? Because that's the next thing that we discovered. Now we're going to do a little bit of substitution to get the other equations. We're going to do some substitution to get the other equations. All right. What is time? From that equation, what is time? Tell me what is time. From that equation, tell me what is time.
Time equals Vf minus V1 divided by acceleration.
Vf minus Vi over acceleration. Is that clear? Now I'm going to bring that. I'm going to bring this time and put it here. I'm going to bring that time and put it here. So what happens? What happens? X is equal to Vf plus Vi over 2 times that time. Vf minus Vi over A. So what I'm doing is I'm trying to eliminate the time. So I get an equation without time. So X becomes, what is Vf plus Vi times Vf minus Vi? Vf square minus Vi square. The difference of two squares. A plus B times A minus B is A square minus B square. You're all familiar with it, right? Over. Now cross multiply that. So we get Vf square minus Vi square is equal to 2ax. So therefore Vf square is equals to Vi square plus 2ax. That's going to be our third equation. Do you understand where this equation came up from? Do you understand how we derived this? Simple. Got the time from here, substituted here, and simplified it to get that equation. So we got that. Now what we're going to do is, we're going to take this Vf from here and substitute it here. I'm going to take that and plug it in here. So what happens? If I take this Vf and plug it here, your equation is going to be X is equal to Vf plus Vi over 2 times time, changes into Vi plus At, that is for Vf. I've substituted for Vf as this. I've replaced this Vf with this. And then the rest of it, plus Vi over 2 times time. That is X. So I'm just substituting this Vf into this. Now X is equal to, so we have now 2 Vi times time. So 2 Vi times time plus At times time. That is At squared, all divided by 2. Now if I divide each of this with 2, I get my equation. X is equal to, what is 2 Vi? What is 2 Vi? 2 2 VIT divided by 2. VIT. What is AT squared divided by 2? Plus half AT squared. So AT squared divided by 2, I'm just leaving it as half. Right? Because this is 1 AT squared divided by 2 becomes half of AT squared. That's our equation. X is equal to VIT plus half AT squared. That's my fourth equation. These are called the equations of uniformly accelerated motion. With these equations, you can solve any problem, any complicated problem. We just use these equations. But how to use it, when to use it, is what I'm going to tell you next. Okay, so I've derived all the equations from scratch. So no need to think about them as, oh, I was given this equation to use, and so I have to memorize it. No, I've gone into the basics of acceleration and then displacement and substitution, got these. Now, how many different variables do you see on the board? How many different variables do you see on the board? How many different? 5? Is it 5? What are they? So we have VI, VF, acceleration, displacement, and time. We have 5 variables only to play with. There's no other variable. In kinematics, these are the main things. Displacement, initial final velocities. Out of these, which of them are vectors and which of them are scalars? And why we are concerned about it is because scalars don't have negative signs. You get it? But vectors do have positives and negatives. Yeah.
Time is scalar and everything else is vector.
Very good. So time is scalar, and all these are vectors. That means what? Time cannot be negative. You're going to get answers as positive time. So in case you solve an equation and suppose you bumped into a quadratic equation, and then you solve the quadratic equation and you got a negative time and a positive time. Take the positive time, throw away the negative time. You get it? Yeah.
Can you explain why X is a vector?
X is a displacement, which means it can be that way or this way or that way or downward, right? So X is the displacement, which means what? From the starting point to the finishing point. So if I throw this marker and caught it there, it's a positive displacement. Because it was here, now it went there. If I threw the marker from here and it came down, it was here, now it is here, that is a negative displacement. So these are all vector quantities, which means handle them with care. If I say I'm throwing something upward with some initial velocity, that will be positive, because I'm throwing it up. If I throw something downward, if I drop something like this, if I drop it, what's the velocity? What's the initial velocity when I drop it? Look, 0. You get it? Yeah.
So when we're studying physics overall, would you say vector quantities are more common than scalar quantities?
Not necessarily, but at least in the equations of motion, vectors are more. Yeah, there's only one scalar quantity, time. But all these are vector quantities because we are conscious of directions. Objects can be going up and down. Final velocity is the velocity with which it finishes the journey. Like if I'm going to drop this down like this. What's the initial velocity?
0.
What's the final velocity supposed to be like? No. Final velocity is just before hitting. Initial is just after starting. You understand? So don't consider the final velocity as when it lands. In that case, everything is going to be 0. Because that marker is at rest here and is at rest here. So you can't take that. So what you take as initial is just before you released. Just before means on the release. What is the velocity? That is considered on the release. That's the initial velocity. And what do you consider as final velocity is on reaching the destination. What velocity was it landing with? You get it? What velocity was it landing with? That is our final velocity. Like a football is caught by a receiver. You can't say that final velocity is 0. It was moving with a certain speed when he intercepted it, right? So you need to know that speed as a final, the speed with which he was catching it. He didn't catch it with 0 speed. He caught it with some speed, right? Or velocity. So there are 5 variables altogether. How many variables are here in this equation? 4. 4 variables are. How many different variables are here? 4. How many different variables are here? 4. And how many here? 4. All of them have 4 variables. Watch. All of them have 4 variables. If I know the first 3 variables out of the 4, can you solve for the last one?
Yes.
That's simple as that. You have 4 variables in one equation. If you given information about 3 things, then the 4th one can be found out. So all you need is 3 pieces of data. Then you can just explore everything else. You get it? Now what is missing in those equations? What is missing here? Which variable is missing? X missing. What is missing here? This is missing in A. What is this missing? And what is this missing? Right? So if you're given a certain problem, all you need to do is search for this information. So a quick problem, let me give you this. I threw the marker upward at 10 meters per second. Watch. I threw the marker up with 10 meters per second and it comes back to my hand. That's all the information given to you. Question, how long did it take? How long did it take to come back? I threw the marker up at 10 meters per second and it landed on my hands. So let's look at the information. I threw the marker at 10 meters. What is that? Positive 10, negative 10. Positive, because I threw it up. What else do you know? Acceleration is the acceleration due to gravity. And I'll talk about it in the next class. Acceleration due to gravity is negative 9.8 meters per second squared. It's always negative. Why? Because the earth is pulling downward. So when something is moving up or down, the acceleration is going to be always negative 9.81 if you're talking about vertical motion. What is the other piece of information that I already told you? Displacement, what is it?
0.
Good. Because it went off from my hands and it came back to my hands, displacement is 0. And what is that I'm asking for? Now, what is missing in all these things? So, pick the equation where final velocity is missing, that is this. And just plug it in. X is equals to VIT plus half AT squared. X is 0, then it becomes 10T minus half of 9.81 T squared. And so if I flip it this side, it becomes 4.9.
Alex.
Can you solve it?